Hi everyone. So in previous videos, we achieved a massive 2x speed up by moving our convolutional mask into the constant memory. But if you look closely at how our threads access the main input memory, here, we're still committing a sin of GPU programming, redundant DRAM access, right? Because our convolution using a sliding window, the adjacent threads are fetching the exact same overlapping elements from our slow off-chip global memory. So today we're going to fix this by actively managing the GPU ultra-fast on-chip SRAM, known as a shared memory. I think we have mentioned this before in the sum reduction example, so it's a good time for us to review what we have learned at that place. So, so what is shared memory? The shared memory is like a private whiteboard for a thread block. Instead of every thread walking to the warehouse, the DRAM individually, we want our block of, let's say, 256 threads to collectively fetch the data once, write it on the whiteboard, and then compute everything from there. All right. But there's a massive catch, the hello problem or the ghost problem. If our block computes 256 output elements and our mask radius is straight, okay, the threads on the edge need to look at the data outside the 256 element chunk. So totally we need to load the 262 elements into shared memory, but we only have 256 threads to do the work. So how do we solve this? Yeah. So so that's something we want to talk about in this video. But before we even touch the GPU kernels here, let's go to the main functions first. So here, okay. So we apply a brilliant strategy on the CPU side called zero paddings. So previously our input array is M, but now we kind of extend the input array on both sides, right? And add some paddings. And the padding is the let's say the mask length is 7, then the padding on each side R is equal to 3, right? So the total array now is n plus 3 times 2, so it's n plus 6, right? So, okay, so we have these paddings. Then if it's the ghost cell, the hollow cell, then we set the values of these padding elements to 0. Instead, if it's within the original array, right, we can assign random numbers. Okay, so then if we have this, then we do not need that kind of complex if-in statement inside our kernel to check for array boundaries, right, which cause the warp divergence. We allocate a slightly larger arrays on the host, okay, on the host. We physically inject zeros to the padding elements. We're treating treating kind of a bit of tiny space for massive gains in the execution time. So you will see that in the with paddings, then within the kernels there will be no if conditions within the for loop, right? Okay. So that's the first point. Then let's look at the kernels. So within the kernels, I think this line is our new lines, right? So we declare our dynamically sized shared memory using the external underscore underscore shared underscore underscore, this kind of keywords, right? So, and then to load the 262 elements using 256 threads, right? The number of threads is less than the number of elements we want to load. We then use our two-stage collaborative loading strategies. Okay, so the 256 threads first here. For each thread, we just load each element, right? And then there are some kind of elements which are left, right? And Let me add one more sentences for the first stage. So in this stage, in stage one, every single thread grabs exactly one element from global memories. It is perfectly aligned, 100% coalescence, and fills the first 256 slots of our shared memory, right? Shared memory. And then in stage two, we need to load the remaining 6 elements. So 262 minus 256 equals to 6. So in stage two, we need to load the remaining 6 elements. The hello cells, we need to calculate the variables called the offset. So offset is our destinations, right? So it's our local destinations for the shared memories. So if the, let's say, thread is 0, then the offset is 256, thread IDX is 1, then offset is 257, so on and so forth, right? Okay. And then the embedded is I think we already calculated, so the embedded is just 262. Okay. Okay, so because let's say for thread 0, because offset is 256, it's less than embedded. Then it will go into the second stage and kind of load one more element. Okay, fetch the global element and put into the 256 of the shared memory slot. Okay. And let's say there's another thread, maybe the thread IDX is 10. So then the offset is 266. The offset is larger than embedded. Then the thread 10 will not do any works, right? It's the if condition will fail. So this thread will just rest, which means we only force the first 6 threads to do the extra work and keep the branch divergence to an kind of minimum status, right? Mm-hmm. Okay, so yeah, that's the case. So you might be asking, is this safe? Won't those offsets cause out of bounds memory crashes? First, it's not. So this if conditions is very important. It checks strictly and prevents threads from writing past the end of the shared memory, right? And because we explicitly padded our global memory array on the CPUs, our global reads perfectly hit the final padded zeros without even causing a segmentation fault. Okay. So we read the necessary elements to the shared memory, and we have to synchronize the threads. That we have seen this before. Okay. This barrier forces all the fast threads to wait for maybe the 6 overtime stage 2 threads to finish writing the hello elements. So without this wall, we would suffer some kind of data race conditions. So we synchronize the threads, and then we can do kind of local submat. Okay, this is the final computational loops. It's beautiful, right? Now we do not need the if condition checks. There are no boundary checks. There's no divergence. Every single piece of the data is fetched from ultra fast on-chip SRAM. So the S array here, yeah. So now this is comes from what? Comes from shared memory, and this mask is come from constant memory. Everything is perfect, right? Okay. So and then finally we write it back. So that's pretty much what we have here, right? I know this logic kind of complicated here, but uh, uh, if we try to understand uh, more, then you will find it's not that difficult. I even built a new file called 1d underscore tout.md file. Let's open it and see what I wrote here. Okay, so this is a scenario setup. This is a scenario setup. We have this kind of numbers for setup. Then let's just trace the thread 0 and the thread 10. Okay, and how the kind of local variables in the registers are changed during this process. Okay, and then I ask 2 questions. Will it go out of bounds? Okay, for as shared memory, no, we have that if conditions, right, to check. But for the global memory arrays, remember, we have, in this case, we have 2 to the array size 2 to the 20. Okay, so it's 2 to the 20. Which means we have exactly perfect number of blocks, right? And each block have 256 threads. Okay, yeah. So if you hear, yeah, it's n the perfect multiple of the block size. Okay, so then we don't need to worry about we have to add, something else at the end of the arrays. I know some people might have such kind of questions. So yeah, I hope this document will help you understand what happens during the uh, convolutional stage, right? You can just pick up, I just pick up 2 threads in the first block. You can, of course, definitely pick up 2 threads maybe from the second block or from the third block, right? And you can try to trace how the values change um, during these kernels. But basically, I think the most important point is this offset and the G offset. The G offset is the source, right? It is kind of the element you want to fetch for your shared memory block, right? And the offset is a destination. It is the local destination of your shared memory block. So that's why we have such kind of um, equation. Okay, since we finished the coding part, let's compile and see the results. So the results are very interesting. As you see from the screen, I have compiled the 1D Taut. It's a Taut version with the shared memory. Okay, and then here are the results. So actually, if you compare with the results of the kernel uh, of the Taut version with the previous constant memory version. So this is a constant memory version. Okay, here. So you see that we add some shared memory functionalities. I mean, both of them have the constant memory. Yeah. And we add some shared memories. Then we didn't see any benefits here, right? So the constant memory takes, I think, 12.7 millisecond, and the the shared memory version takes 14.3 seconds. Yeah, so it didn't get faster. So hardware kind of uh, it depends on some hardware generation, and it seems like we do some over optimized right versions. Okay, so there might be some reasons that I can try to explain here. First, the power of the modern L1 cache. So in the older tutorials were reordered on the old GPU architectures, I mean the next tutorials. But on modern GPUs like the Emperor or ADA RTX 4000 that I'm using now, the hardware L1 cache is incredibly smart and massive. In physically, the L1 cache and the shared memory are covered out of the exact same piece of kind of silicons. So when our previous constant memory kernel asks for data from the global memory, the hardware already automatically and invisibly cached those overlapping elements in L1. So we programmers in the previous examples, we programmers do not cache it manually, right? But actually the hardware already automatically and invisibly cached those values. Yeah, so it's kind of one reasons, right? And if you check the code of the convolutional uh, kernel between the constant memory left side and I think the Taut version on the right side. Actually, you see a bunch of kinds of overhead of the Taut versions, right? You have to calculate embedded offset, G underscore offset, these things. And the most important part, we have to synchronize the threads here. Okay, yeah. So um, so even if we do not have the kind of if conditions, we add a bunch of other overheads, and yeah, so it seems like we have to pay some kind of management fees, right? For using the shared memory manually. Yeah. So that's the second reason. The third reason might be the arithmetics intensities. So basically, the arithmetic intensity in this problem is pretty low, right? We forced our threads to carefully load the data, organize it, and synchronize it. But after the data preparation, we just run a loop just 7 times, right? And to do 7 multiplications. So, uh, yeah. So, that's kind of ridiculous. Um, so the return on this investment simply isn't here. So yeah. So does that mean the shared memory is not used for? It's not. Shared memory is the most powerful tool in the CUDA, but it's not a silver bullet. It shines in algorithm with high arithmetic and intensities, like the matrix multiplication or 2D image convolution. We will see a kind of 2D convolution example in next videos. Um, so in these cases, a single piece of data is loaded once and reused hundreds of times, right? Instead of just maybe 7 times here. So, um, so some kind of broader ways is the data doesn't lie. Profiling is the only truth in the GPU optimizations, right? Maybe we have some kind of theory behind, but actually we have to compile, run code, check the profiling data, and we will know whether what we added is really helpful or not, right? So, um, yeah, I really like these examples. I mean, all of you enjoying that. And thanks for watching. See you in the next video.